Wow.
And another step there.
I do know that I think it needs to be encased by the positive and negative charges.
Of course, that's not going to clean up the environment. So finding ways to make clean electricity is really important, and that's of course what we do here. And why fusion? This is the holy grail, the ultimate way of making electricity one day. We don't turn a turbine yet. Why? Because we are sticking together essentially forms of hydrogen. So our fuel is water, of which there is plenty, especially in the UK. Cleaner than burning fossil fuels, we don't release any carbon. Now that's the same as renewables and fission, which is splitting apart heavy atoms. Unlike fission though, this is an inherently safe process. You are making a miniature ball of gas, 150 million degrees C, a very small amount of it inside a chamber. If anything goes wrong and it touches the chamber walls, the chamber will instantly cool the reaction and the whole thing stops in a heartbeat, really, really quickly. That is difficult to get over in a physics sense and an engineering sense, but inherently safe. If anything goes wrong within the inside of this reaction, it will stop itself. And it will give you a very large continuous power supply using very little fuel. The process of fusion is immensely efficient in terms of mass of fuel. We predict that a 2 gigawatt fusion power station on the grid, let's say 2050, would use about 400 kilos of fuel a year, 400 kilos of heavy hydrogen a year, which is 10 million times less than the amount of oil or coal or gas you put into a conventional power station. So incredibly efficient, large power supply. You think, well, if that's great, why on earth isn't it here? Will it work? And crucially, will it be economic? Can we do something one day that is economically viable? Will it be available enough and produce electricity at a price that you're all willing to pay? And that's the kind of challenge we have with it.
Our other device, MAST. So a little bit of admin before we get started. As we're going around tonight, particularly on this side of site, there may well be work going on tonight right up until the end of the evening, up until about 10 o'clock. So this is a working site. There may well be work going on, and particularly in the operational areas that we'll go into a bit later on. There may well be work going on, forklifts, lifting activities, etc. So just keep your eyes open around you, just be aware of your surroundings, look out for the kind of needle stuff, forklifts, trip hazards, the usual kind of malarkey, and just, while you're looking around, just be just wary of what's around you. Also, again, particularly in the operational areas, you will see signs on some of the equipment warning you of either radiation hazards or hazardous materials contamination. So if you do see a skull and crossbones on something, don't lick it or put it in your pocket or anything weird, please. They are there for your protection. Don't cross any barriers, push any buttons, pulling levers, the usual kind of stuff. Just be wary, they're there for your protection. Some of the stuff you really don't want to swallow it or inhale it or get it on your skin. So just respect any barriers, respect any signs. Also, as we're going around tonight, nothing you're going to see tonight is commercially sensitive in any way. So if you can see it, you can take photos of it. You don't need to worry about that. And finally, as we're going around, if you do have any questions at any point tonight, please do just stop me and shout them out. Just interrupt me. Don't feel like you need to wait for a natural pause or a break in the conversation or whatever. Just interrupt me and say, hey, what's that? Or how does that work? Or what does that mean? You'll get far more tonight. So don't feel any need to be polite, just interrupt me. I think that's everything. So we're starting in a little bit of an unusual order. So this is the jet control room. So I'm going to show you a bunch of stuff in here, explain to you when we get back to the models, the fun ones of how Tokamak's going to work, and then we'll take you actually out onto the plant and show you some of the operational areas and show you the actual machine itself. So this is the control room. This is where we operate the jet from. Now we are technically in an operational campaign at the moment, although as you can probably guess the machine's not running right this very minute because we're still in restart. But this is when we go into full-scale operation. This is where we actually operate the machine from. So normally this would be this would be jam-packed full of people. So we've got all our physicists, all our engineers for running the individual plant systems. So in the centre there, in front of that project screen, that's where the key people for a particular day of operations will sit. So then you have the session leader, who's the chief physicist for that day of operations, and they're responsible for scheduling experiments that go on the machine and looking after a team of physicists and looking at raw data that comes off the machine as well. And that's a lot of data as well. So a single jet pulse will generate on the order of around about 60 gigabytes worth of raw diagnostic data. And bearing in mind your average jet pulse is around about 60 seconds long, you're talking roughly a gigabyte per second of operations for the machine. And we have to keep all the data produced right back to the very first pulse that was run on jet back in 1970 something. So as you can imagine, over 30 odd years, that adds up to an awful lot of data. So jet's produced around about 1.5 petabytes worth of total data over its life. So to give you an idea, in case you're not aware, petabytes, 1,000 terabytes, terabytes, 1,000 gigabytes. Now to put that into context, so that's over Jet's 30-year operation. I gather you had a little bit of introductory talks before this, where Chris went through, did he mention ITER? The bigger brother to Jet under construction in South France? So ITER, so we produced around about 1.5 to 2 petabytes of data over 30 years worth of operation. ITER are expecting to produce 4 to 5 petabytes of data per day of operations. Quite what the hell they're going to do with it all is beyond me, but that's their problem. It gives you an idea, these big physics experiments, they do produce an absolutely enormous volume of data.
Where do you store the data? Do you have your own data center?
So we have two. So one is in that server farm at the back there. So we keep multiple copies for redundancy purposes in case if they burst to the ground or whatever. So our main copy is in that server farm at the back there. So that's all stored on tape.
Yeah.
That's the kind of long-term storage, but we can call that up into I forget what they call it, but it's a system for keeping. We keep something like 100 gigabytes worth of data in quick read access memory for when physicists are working on models, kind of day-to-day work. They can request something from the archives. It takes about an hour to recover it from tape. And then the other location is down at Harwell. So they've got another data center down there, which isn't exactly what we've got here. So they serve two purposes. They serve us, and they also serve as one of the data centers for CERN as well. So for the LHC, it's about, I think, 12% of the data from CERN is stored at Harwell as well.
So you wouldn't use cloud because it's not secure enough?
There's a couple of reasons. One, sheer volume, and the read-write speed isn't high enough. So for the kind of work we do, we're producing 60 gigabytes, sometimes more than that. It's more like 80 gigabytes these days, actually, per pulse, and we're running a pulse every half an hour. And at the same time, you're also trying, you've got maybe 100 physicists on site who are working on physics data from pulses across the whole 30-year worth of operations. So they're requesting it pretty much constantly. There probably is a security element to it too, although that's a little bit beyond me. That's kind of the IT guys worry about that, and but I gather there is some
risk.
Probably more paranoia than anything else, but volume is the general prohibitor for that. So as you can imagine, a machine the size and power of Jet, we do consume quite a lot of power here at Culham. So to give you a rough idea, like I said, the average jet pulse is on the order of about 60 seconds long. During that 60 seconds, we will consume roughly, so midway through a pulse, peak power, we will consume around about 1,000 megawatts worth of power, or a gigawatt worth of power at that peak draw. And that represents around about 3 to 4% of the entire national grid's output for that 60-second period, to give you a rough idea. Unfortunately, we're only actually allowed to take around 575 megawatts, for about half the energy we need off the national grid at any one time. Otherwise, you cause raging blackouts in Oxfordshire, and the national grid get very, very cross. So the rest of the power we need, we get from a pair of massive flywheels right over on the other side of the site. So the great big things, about 9 meters in diameter, about 2 meters thick, and they weigh 775 tons apiece. And we spin them up to 225 RPM in a few minutes leading up to a pulse. And they store around about 3.5 gigajoules worth of energy each, and they will each give us a peak power output when we first flip the pony motor of around about 400 megawatts each, which means for a brief period they're putting out about the same amount of power as Hinkley Point. To give you a rough idea, it's an enormous amount of power we need to run this machine. And that represents around about 6 megawatt hours worth of electricity to actually run a single pulse, which is fairly meaningless. That's about 400 pounds worth, to put it another way, for that 60-second pulse. And that's to get up to these really, really extreme temperatures that we need. So I don't know how much Chris covered in the talk at the beginning.
150 million.
Exactly. I mean, that's a minimum, really. And we have been known to go up to 300 million. in some particular pulses. So heating the plasma at those temperatures, you can imagine, uses a huge amount of energy. Probably one of the most interesting things you can talk about before we move on are these video feeds. Now, you can probably guess these are not live, but these are, I believe, from one of the pulses from the previous campaign, and you can see from the clock at the top there roughly how many pulses Jeff's run over it live. And it's worth noting these two and this one, these are in the visual spectrum. So this is what the plasma does actually look like to the human eye. This one's in the infrared spectrum, so that shows you all the hot spots in the vessel. These two are a little bit more accurate in terms of the coloration than that one. And again, you'll note from the timestamp at the top, the average pulse is on the order of around 60 to 70 seconds long. Unfortunately, it's not very long, so I have to talk quite fast, but it ticks over at around about 78 seconds. So confidently. There we go. So you can see it's about 40 seconds into a pulse, which is when we actually strike the plasma. And at this point here, that's when all of our secondary heating systems come online. So that's when the neutral beam heating systems come online. So this is peak power now. That's your 1,000 megawatts, 60 megawatts for feeding power. You see all these kind of little white flashes on the screen? That's not signal interference. That's actual neutrons hitting the camera lens. So it's one of the ways you can actually tell there's fusion going on inside the vessel. Is every single one of those little white flashes represents a fusion reaction that's happened, neutron that's been given off, and that neutron's actually going to hit the camera lens. And then this one gives you an idea of what that does to the camera sensor after a couple of years worth of operations. You do have to replace the cameras quite frequently. And you'll note from the video that you're only really seeing this kind of like halo ghosting effect around the edges of the plasma. There doesn't appear to be anything in the core here, and that's a bit of a misnomer. Because what you're seeing around the edges here is actually where the plasma is coolest and least dense. The hottest, most dense part of the plasma is actually in the core here. But it's so hot that it's not emitting in the visual spectrum. Because emission frequency is linked to temperature, right? So you guys are all currently emitting in the infrared spectrum. So if we heated you up by a few hundred degrees, you'd start emitting in the visual spectrum. If we kept going up into the tens of thousands, 100,000, millions of degrees, eventually you get to the X-ray spectrum. And that's why you can't see the bulk of the plasma, is because it's actually emitting X-rays, not visual light. And what you're seeing around the edges is only where the plasma is coolest, and it's only a few thousand degrees. And you can tell quite a lot from the coloration of the plasma as well. So this kind of very reddish colour that you see is generally indicative of when you've got just ionised hydrogen in the plasma. So the emission frequency for ionised hydrogen is a very, very red colour in the visual spectrum. So when you get a red plasma, that generally means you've got a high purity, high quality plasma. You've basically got just the hydrogen, oxygen, and fuel and not much else. These more kind of bluey, mauvey colours you see in some of the videos are generally indicative of the carbon and oxygen impurities in the plasma. So you can generally tell a reasonable amount from just from the coloration of the plasma. And you'll note when we end the pulse, if you watch carefully, you see a little ball form here. And that's how we actually end the pulse in a controlled manner. Rather than just turning the magnets off and letting the plasma go wherever the hell it feels like, you use the field to actually ball the plasma down into a little tight sausage up against the inner wall, which you'll see round about now, and it disappears. And that's what we do. We ball it up into a little tight sausage and splash it against the inside wall, and dissipates all that heat over a nice large area, save overheating any of the wall tiles. Any questions before we move on?
So Chris mentioned, I think I heard him say that it was using the neutrons that you would regain or recapture energy for actual, if you were turning it into viable energy. So how did that work?
Yes, so that's kind of one of the things that people often don't factor in, is they assume that because we're operating at such extreme temperatures, the heat you'd extract for power generation will come directly from the plasma itself. The 100 million degrees worth of plasma you've got sitting in there. But the actual mass of the plasma you've got in the vessel is only about 4 grams. There's not a lot of actual physical mass of plasma in there. So at those very high temperatures, there's not a lot of thermal mass. So the bulk of the actual energy you get from for extracting power, or at least what's proposed, because it's not actually been done yet, the theory is that you use the neutrons that are coming off, and you coat the inner wall of the machine with lithium-6. So essentially you have a blanket of lithium-6 that coats all but the very, very base of the machine here, which is known as the diverter region. For various reasons you can't coat that region with lithium, but the rest of the machine you coat with a blanket of lithium-6, and under neutron bombardment, lithium-6, fortunately, tends to absorb those neutrons and form lithium-7, which is unstable, and it beta decays into tritium and helium-4. So by absorbing that neutron energy, that energy has to go somewhere, so it goes into heat. So it heats that lithium blanket, and it serves 2 purposes. And that heat goes into the blanket, you run a coolant through the blanket, and that's how you get your heat output. and then you take the heat out, boil steam, 10 turbines, the usual kind of stuff. And the second thing that does is because it is exactly so it's a breeder reactor as well, so it also breeds your tritium fuel. Because I don't know if Chris covered it, but tritium is one of the fuels that we plan to use in a commercial reactor. So tritium is just another form of hydrogen, it's super heavy hydrogen. Okay? So you have deuterium, heavy hydrogen, and tritium, super heavy hydrogen. You slam them together and they form helium-4 plus a spare neutron. Now the problem with tritium is it doesn't really exist in nature because it's self-unstable, it decays, it's radioactive, and it beta decays. And it has a half-life of around about 12.5 years, which means any naturally occurring tritium decayed kind of millions, billions of years ago. So it doesn't really exist in nature except in very, very trace quantities. So any tritium we plant we have to synthesize it artificially. And that's why essentially you need to build a breeder reactor. So that's what the purpose of the lithium blanket does. It acts as your breeding volume and it also acts as your power extraction plant. Okay? Right, so before we get kicked out, so this is a very basic model of jet, but it's quite useful for pointing out some of the key fundamental components and principles of how a Tokamak works. So jet is what we call a Tokamak. A Tokamak is a particular style of fusion device. And the whole plethora of weird and wonderful fusion devices, but the most common are magnetic confinement devices, and of those, the most common and generally accepted to hold the most promise for power generation are Tokamaks. And Tokamak is just a Russian acronym for something totally unpronounceable, but it literally translates to toroidal chamber magnetic field, which is a very literal description of what jet is. It's a toroidal chamber, torus being the mathematical name for a donut. It's a toroidal chamber, and it has a magnetic field. Very literal description. Now, Tokamaks, in the most basic sense, are really just... Actually, before I tell you, does anybody want to hazard a guess as to what these big orange things are? I told you they were laminated soft iron. Electron engineers in the room?
This should transform the whole thing, surely.
Boom, exactly. So these are essentially the core of a transformer.
Yeah.
So all Tokamaks, or virtual Tokamaks in the most basic sense, are just high-tech transformers. So how familiar is everybody with how transformers work? Relatively? Not at all?
Familiar.
Some? Maybe? Getting nods, good. Okay, Grant, that means that I'll explain it. Obviously in a normal transformer, your primary winding is a physical winding of copper cable, right? So on jet, the primary winding is a central solenoid that runs through the middle, okay? 1440 turns of copper cable. We run around about 50 kiloamps through that central solenoid. That produces magnetic flux in the limbs, and then that induces a current flow in the secondary winding. Now on a normal transformer, the secondary winding is again a physical winding copper cable. On jet, the plasma itself actually acts as a secondary winding. So it's essentially a single turn secondary winding. So you have a 1440 to 1 turn down ratio. So that 50 kiloamps ends up inducing a current to flow in the plasma itself of anywhere up to around 3 to 4 megaamps. Now that serves three main purposes. How we actually generate the plasma in the first place, because again, how familiar with people are what a plasma actually is on the kind of atomic scale? Getting some blank looks, some nods. Okay. So plasma is essentially a highly energetic gas. Okay, so it's a gas, it's similar to a gas, but where the electrons have so much energy they're no longer orbiting a specific nucleus. Okay, so it's a highly energetic ionized gas. Think of it that way. So when we inject the hydrogen into the machine, it starts off in gaseous form. What we do is we put this huge magnetic potential on that gas. And there are enough atoms in the machine that random probability, random chance, says that one of them will happen to collide with another one and cause it to lose its electron. Physically, not the electron off the other atom. At that point, that atom is then charged. It's an ion, so it then gets accelerated by that magnetic field that it's sitting in. As it's accelerated, it then hits another atom and causes it to lose its electron, and then that one gets accelerated, and so on and so on. You get this kind of cascade breakdown effect. And that's how we actually turn it from a gas into an ionized plasma in the first place. And the second thing it does is it gives us our initial heating burst, because whenever you run current through any normal conductor, it gets hot. And the plasma is no different. And it turns out when you run 3 million amps of current through something, you get pretty damn hot. So that gets us up to around about 30 million degrees, just using the kind of resistance of the plasma alone to heat it. Sorry, 13 million. And the third thing that plasma current does is it also helps to actually generate the magnetic confinement field. So again, whenever you run a current through a conductor, it produces its own magnetic field, and the plasma is no different. And that current that's flowing around that, in this kind of toroidal direction around the machine, that produces a magnetic field that acts in this kind of cross-sectional direction. It's what we call the poloidal field direction. And that essentially produces that initial magnetic bottle that pulls the plasma away from the walls and confines it. And then we've got a bunch of coils here, which are the colloidal field coils, which are there to boost that field generated by the plasma current. And they're primarily used for positioning and shaping the plasma inside the vessel. Now, in addition to those, there's a secondary set of coils, which are these D-shaped coils here. There's 32 of them around the machine. And then there is the toroidal field coils, because they produce a field that goes around the torus. And they essentially produce that circular path around the machine for those ions to follow. And then those two fields, the toroidal and colloidal fields, they actually combine to produce a net helical field. So the final field shape is actually a toroidal helix. So the best way to visualize it, imagine you take a slinky, right, and you join the ends together. That's very much what the actual magnetic field shape looks like inside the plasma. And to make it even more confusing, charged particles, ions, I don't know if you're aware, they don't follow magnetic field lines linearly. They don't just go along them like a road. They process, they orbit around those field lines. So it means each single ion within that plasma is following a helical path around that helical field. So you have this kind of double nested that. You have to see an animation of it really to fully appreciate it. But that's what the plasma is actually doing that you don't really see in the video. It's actually kind of twisting and spiraling as it goes around the machine. So very, very quickly. We've got a minute left. To bring you over to this other model, which is a much more detailed model of jet. And this is a pretty accurate representation of how jet looked right up until around about the mid to late 90s, which is when they stopped bothering to update the model. And then you've got a European average man and woman there for scale. And the most important thing to point out on here is this big grey tower here. I mentioned that the plasma current only gets us up to around about 30 million degrees, just using the resistive heating alone. Obviously we need about another 100 million in order to even start achieving fusion. And the bulk of that comes from this system here. So there's two of these towers, one here and one 180 degrees over on the side that's cut away. And these are what we call the neutral beam heating system. So they are essentially particle accelerators. So each one of these beam lines, these 8 beam lines here, contains what we call a pinning, or positive ion neutral injector for short. And we take a gas, most commonly deuterium, and we ionize it. We strike an electric arc through that gas, and it strips off the electrons from those atoms and leaves behind positively charged deuterium nuclei. Positive because they're missing an electron, yeah? Because they're charged, we can then accelerate them in a DC field between a pair of charged plates. But unfortunately, because they're charged, they won't actually penetrate the bulk magnetic field that surrounds the machine. They'll just be scattered in the beam line. So we have to neutralize them again. Hence why they're called neutral beams. So we pass them back, after they've been accelerated, they pass through a second gas, which gives them back their electrons. So they're then neutrally charged, and they can then penetrate the magnetic field that surrounds the machine and enter the vessel. And they deposit energy into the plasma literally just by colliding with the ions that are in the plasma. And those two beams sets combined, the 16 injectors together deposit around about an additional 25 megawatts worth of heating power into the vessel. 25 megawatts, a fairly meaningless number without context. To give you a rough idea how much 25 megawatts really is, are you all familiar with the TGV? High-speed train, intercity train in France, yeah? So fully laden, TGV weighs around 450 tons. Full speed, 190 miles an hour, roughly. The kinetic energy of that intercity train is roughly equivalent to what the neutral beams will deposit into the plasma over a 60-second period. So it means every 60 seconds you're essentially crashing an entire high-speed train into the plasma. And bearing in mind the plasma only weighs about 4 grams, so the weight of a postage stamp in its entirety, it gives you an idea of just how much a colossal amount of energy is actually being deposited into that plasma, and that's how we get the bulk of that additional heating power from. Now, there is a tertiary system which is known as the ICRH, which is another system, which is the ion cyclotron resonance heating system, which is a great name, which is basically a radio frequency based system. So you fire radio waves into the plasma and they deposit about another 8 megawatts worth of heating power as well. So there's actually 3 different systems that we operate during the pulse. Sorry, we've got to move on briefly, but if anybody's got any questions,
were those added incrementally, or did you design?
Fairly lucky tonight that the children are still open with their access, because we're technically supposed to be operating at the moment, but they've had a pause in operations, which is why the doors are still open, so we're quite lucky tonight actually. Just before we go in, when I take you through into the Taurus hall, even though you can get pretty much right up to the machine, there are so many diagnostic systems and heating systems on the machine that you can't actually see the banker vessel itself, or the plasma chamber, if you like. So it's difficult to get an impression of actually how big the plasma chamber itself is. So this facility behind me, this is what we call the IVTF, the International Training Facility. Blue's kind of in the name. It's a training facility doing intensive work. You see this kind of slightly greenish looking piece of metal on the side here? That's actually one of the original options from Jet. So when Jet was constructed, the vacuum vessel was built from 8 individual segments, very much like an Orient, 8 of them at the same option. And that is essentially the 9th spare option. In reality, the vacuum vessel itself was so reliable, you never really needed it. So around about the mid to late 90s, they said, oh hey, can we have that? And they built the rest of this facility around it. And that is now essentially a 1-to-1 scale mock-up of the actual vacuum vessel itself. So that is essentially the exact size of the real plasma chamber. So we'll take you out to the cool lip through the window. I'll just give you a very good feel of what inside the machine actually looks like. And we predominantly use this, as you can probably guess, for rehearsing remote maintenance operations. So one of the areas, unfortunately, we don't have time to take you in to show you tonight, is the remote maintenance control room. So being a nuclear reactor, we try and avoid sending people inside the vessel wherever we can avoid it, because nobody wants to be irradiated where they don't have to be. So we try and do the bulk of our particular routine maintenance work using a suite of what we call remote maintenance hardware, or remote handling hardware. They're not robotic systems, but one of the things, one kind of common misconception we get is that the two booms that go inside the vessel are what we call teleoperated manipulators. So there's always an operator in the loop. So there's two articulated booms that come in through ports on the vessel, very much like this one here. And they come in 180 degrees opposed from each other. So one of them, you're actually seeing in that 10 behind you, that's the end of the option 1 boom. There's actually kind of coiled up, it's a very kind of serpentine, that's coiled up inside that enclosure. And when we want to do remote handling off, we pick up that entire enclosure, you dock it onto a port flange, like this one here, except obviously in their room. You drive the boom through the port and into the vessel. And then the other one comes in at option 5, which is that one you're seeing there. So that's the same boom that actually goes inside the vessel. So the option 1 boom carries all of the kind of tooling and equipment for that day of operations that we're going to do. And then the option 5 boom is the one that carries the actual manipulator itself, that kind of prey mantis looking thing on the end there. That's what we call the mascot. Not because it's our mascot, it's another acronym for Italian, in Italian this time that I can't pronounce. But essentially those two booms can reach anywhere on the inside surface of the machine together. So that's a master-slave device. So there's a master unit which sits in the control room, it's about 100 yards that way. And the operator essentially sits inside a replica of that mascot, not physically inside the casing, but you sit kind of inside the arms of it. And it's very much like what you see them doing in kind of ROVs, like in the subsea oil and gas industry. As they move the arms around, those motions are picked up by the control software and then replicated on the slave unit that's mounted onto the end of the vessel. Sorry, on the end of the boom in the vessel. And the mascot does have a force feedback system as well. So the forces and torques that the mascot sees are referred back to the operator in the control room, so they can actually essentially feel the weight of the components they're carrying, they can feel the solidity of them, and the torque of the kind of bolts that they're doing up, and all those kind of things. It sounds a little bit frivolous, a bit excessive, or if you bother, but you don't realise how much information you get through your sense of touch until you don't have it. Particularly when you're doing these kinds of teleoperated, remote controlled operations, the bulk of your sense comes really through that haptic feedback. Because as you can imagine, doing up a bolt is a great example, for instance. So as you can imagine, as soon as you engage the thread of that bolt, you lose all other sensory feedback. You can't see what's happening, you can't hear what's happening, you can't smell what's happening. So really, if you're in your garage and you're doing a bolt up on a car or whatever, all the information you have comes through that sense of touch. So whether it's cross-threaded or it's galling or there's debris in there or whatever, you feel that. And if you don't have that, the first time you know there's something wrong is when you shear the head of the bolt off, and then you're really stuck. So it tends to speed up operations, for one, because as you can imagine, if you're trying to line something onto, say, a valve pin, you don't have to get a camera in up there behind there to see when it's engaged. You can feel when it's locked into place. So it tends to speed up operations and it tends to reduce those kind of low-level, small mistakes that operators make. You know, things getting jammed, things getting seized. And generally they can feel when something's wrong long before you pick it up with something like a torque sensor or something like that. So generally, they'll start doing it all, once you feel right, back it out, have a look, oh yeah, this machine is red. Excuse my French. But yeah, and that's kind of why we have that haptic feedback. It tends to reduce those kind of low-level mistakes. Can I ask you a question on the way down? Is that okay?
Yeah.
We've got another group following us up, that's all.
Yeah.
Why don't you just open the door, stick a man in there with a bunch of spanners?
So in the old days we did.
So what's the benefit of doing it robotically?
There's a few reasons for doing it. Particularly since we started using tritium, is a big one. So tritium and beryllium are the two main hazards to doing any in-vessel work. So tritium, as I mentioned, is radioactive. So the activation levels inside the machine during a tritium campaign and for years after a tritium campaign are far too high.
Right, so it's to do with just radiation basically.
Partly.
Yeah.
So, and now we haven't run a tritium campaign since 1991. So the background radiation levels in the machine are relatively low, particularly once you've done all the kind of electrical isolations and physically opened up the shielding doors. That takes about 2 months. The radiation levels have dropped down to below safe level. You can do in-vessel work. The other hazard is that the people inside the vessel is the beryllium. So I mentioned that most of the wall tiles are made from solid beryllium.
Yep.
The problem with beryllium is, and during operations you inevitably get some dust that's produced. Beryllium is extremely hazardous to your respiratory system. It's a similar effect on your lungs to asbestos, but it's actually worse. If such a thing's possible. So
again,
it's
respirators
really,
and stuff.
Well, full pressurized suits.
So that's cheaper than a robot, surely?
It's not just about cost, it's about to do with safety. So we operate under a principle of what's called a LARP, and virtually all nuclear facilities do. And in fact, a lot of it, general industrial facilities do, and it stands for as low as reasonably practicable.
Yep.
And it basically states that you should reduce the exposure of your workers to hazardous materials as much as reasonably practicable. So it's mainly for safety purposes, and so the radiation hazard is certainly non-zero. Right. So the accumulated dose from the workers inside the vessel it does add up over time. And also, one of our main selling points is the fact that we are currently the only tritium-compatible Tokamak in the world. So if we want to be able to operate with tritium, we have to be able to have a means of doing in-vessel maintenance.
Right.
Because if you do a tritium campaign, you're talking 3 to 4 years before you can even enter the tourist hall itself, this room, before the radiation levels drop down to a safe level. The levels are that much higher during tritium ops. To actually enter the machine itself, you're talking maybe 5 years. So you've got to have a means of being able to fix stuff inside the vessel remotely if you want to do tritium ops. And the other reason is we essentially act as a test station for ITER. Because the problem with ITER is even during their deuterium-only operations, the machine's so big, the levels inside ITER will be far too high, you'll never be able to send people inside the machine. So ITER will never have that backup option if something goes wrong with being able to send people in. So we have to develop those systems now in order to have them to be robust enough and reliable enough for operation in ITER for kind of decades at a time. That's kind of the other main reason, is we do as much as we can with the remote systems so that we learn how to do it with the remote systems. Even when something goes wrong, something gets stuck, we then try and recover it with the remote systems as well. It's absolute last case, last ditch resort is to send people.
Brilliant. Thanks.
Right. As you can probably guess, this is Jet. This is the machine itself. And as you can probably guess, we're not operating at the moment, hence why these big shielding doors are still open. So normally when we're operating, these 2 yellow doors here would be closed. So those 2 doors, they weigh around about 700 tons a piece, reinforced concrete. And you'll notice there's a big gap above that door, and there isn't one above this door. That's because what you're actually seeing there is not part of the wall above the door, that's actually a concrete lintel that stands the full width of the building. And you can see on the other door, that's actually jacked up into the ceiling. And the reason for that is to allow access for the crane to come through. But each of those lintels, they weigh 1,100 tons a piece. So that means you have to move around 4,000 tons worth of concrete shielding just to gain access to the tourist hall in here to do any maintenance work. And all of that is there to shield you guys from the high energy neutrons that are coming off from the reaction, and also X-rays and gamma rays as well. To give you a rough idea of magnitude, were you to be in this room during a pulse when we were operating only with deuterium, your absorbed dose after 60 seconds would be on the order of around about 400 millisieverts. Fairly meaningless number. To give you a rough idea, the UK government says that as a radiation registered worker, we're allowed to receive 25 millisieverts in a year. That's considered to be a safe dose. Even that's a little bit high. We actually work to 5 on site, that's our target. So 400 in one go is really not good. But you'd probably survive. Were you to be in here for a single 60-second pulse when we were operating with tritium, you'd be receiving on the order of 2 to 3 sieverts. So about 20-30 times more. To give you a rough idea, 1 sievert is acute onset of radiation poisoning and is considered to be a fatal dose. And we don't mean fatal as you'll die at 20 years of pancreatic cancer, I mean you'll be dead within weeks. It's like skin melty sort of levels of radiation. You really do not want to be in here when we're running a pulse. Hence why we have all that concrete shielding. And then this zone is also run at a slight depression when we're operating as well. So this room is actually kept at a slight vacuum as well, such that if you do have any breaches on the machine, and some of that tritium and beryllium dust escapes from the machine, is kept within the torusol, air is drawn in, it doesn't leak out, it keeps any potential contamination contained within this room. In reality, the levels are actually very, very low, so it's a precautionary measure. Right down in the heart of that machine is the plasma chamber, which you saw a equivalent size of a second ago, and that's where we generate that superheated plasma. It's a very, very extreme environment going on inside that vacuum vessel, because in order to generate those very high temperatures at those very low plasma densities, we have to keep the inside of the machine at what's called ultra high vacuum conditions. So it's roughly 10 to the minus 9 millibar, if anybody knows their vacuum numbers, or roughly 100 billionth of an atmosphere, to put it another way. Or, to put it a third way, it's roughly equivalent to the atmospheric pressure at the altitude of the ISS orbits at. So basically space. Okay? And in order to generate those very, very low pressures, you can't pump fast enough with conventional kind of mechanical vacuum pumps. So we do the rough pumping using mechanical pumps called turbo pumps. But in order to get down to those very, very low pressures, you have to use a different type of pumping, what's called cryo pumping, which is where you essentially have radiator panels on the walls of the machine and inside these nib boxes, so the neutral beam boxes. Those radiators, we pump cryogenically cooled liquid helium through those panels at around about 4 Kelvin, or 4 degrees above absolute zero, minus 269 degrees Celsius. And at those temperatures, everything except helium, and to a certain extent hydrogen, but mostly helium, will actually freeze. So oxygen, hydrogen, beryllium, all of those elements will actually freeze in the form of frost on those cryo panels. And that's how you effectively pump those elements away. You essentially lock them onto those cryo panels. So you actually get oxygen frost, nitrogen frost. The downside is, as you can imagine, what you've essentially got there is you've got a surface that's sitting at minus 269 degrees C. It's about 3 meters away from the core of the plasma that's sitting at upwards of kind of 150 million degrees C. And that is the biggest temperature gradient in the shortest space anywhere in the known universe. Genuinely. Because the only other place you find those temperatures are in the cores of the absolute largest stars. I mean, that's about 10 times hotter than the centre of our sun. So in order to get to those temperatures, only the really, really big stars have those sorts of core temperatures, and in deep space, which are normally, hundreds of millions of kilometres apart. Inside jet, they're within 3-4 meters of each other. It gives you an idea of just how extreme environment is going on inside that vessel. Any questions before we move on?
Was there ever any plan or future plans to use superconductors for magnetic fields? And cryogenically cool the whole system?
In an ideal world, yes. So the question was whether there was ever any plan on jet to upgrade the coils to using superconducting materials. So I don't know how familiar people are with superconductors. Some maybe. Okay. So conventional copper magnets, as you probably know, whenever you run a current through any normal conductor, it produces heat as a byproduct of its electrical resistance. That fundamentally limits the magnetic field strength you can get to, because you reach a point at which you just end up starting melting, you just melt the copper, right? So it either limits the strength, or it limits the amount of time you can operate at that strength for, because you just overheat and melt the coils. That's one of the things that actually limits the pulse time on jet. You can't run longer than about 60 seconds because you'll start melting the coils, start melting the actual magnets. Now, superconductors are really weird materials that were discovered in around about the late 80s, early 90s, that when you cool them to cryogenic temperatures, most superconductors have to be below about 5 Kelvin. At that temperature, they have zero electrical resistance, like none, like absolutely zero, which is a really weird property, which essentially means that when you run a current through them, they don't produce the same levels of heat that you get from a copper magnet. So you can run a much higher current and therefore much higher field strengths for the same size of coil. The downside is you've got a pump that you've got to cryogenically cool. Now there are Tokamaks operating that have cryogenic coils. So there's one in there's K-Star in South Korea, there's East and West in China, and D3D, Aztec, there's a whole bunch of them. The downside is generally they have to be designed from the ground up to use superconducting coils. One jet, most of the coils you can't actually move them now. Not without dismantling the entire machine, it's just not deemed to be cost effective. And the main thing you get from it is increased field strength. Now that's not really what Jet's high field strength plasmas is not really what Jet's built and designed to test. There are other machines that are better designed and better suited for those types of experiments. The main selling point of Jet is the fact that you can run tritium with it, which you can't, there's no other machine on the planet that can currently use tritium. So that's the main selling point of Jet. So from a cost benefits perspective, you can do it, sure.
ITER, is that getting cryogenically cooled?
ITER is, yeah. So ITER is planned to be cryogenic. So they are using superconducting coils. So they're a mixture of niobium tin and niobium titanium, if you're interested. And incidentally, there are materials that will allow you to run them at higher temperatures, what we call high temperature superconductors, that don't have to be cooled with helium. They can be cooled with using only liquid nitrogen, which is around about 70 Kelvin, which is a lot more cost effective. The downside is all of those are ceramics. So you have yttrium, barium, calcium, copper oxide, and bismuth, strontium, calcium, copper oxide, which are the only two high temperature superconductors. But they're ceramics, so they don't have the same material properties that metals do. They're obviously very brittle. It's very difficult to work with when you're trying to build high strength coils.
And this is 1979, or 1983 really.
Yeah, mid-1970s. So most of what you're actually seeing is not original. The only things really that are original are the vacuum vessels and the nibs. Virtually everything else has been upgraded over the time.
So initially we're going to start here in the control room and just looking at a typical Mars pulse and also explaining what we do on a normal daily basis. We'll then head over and just show you some of the components from the machine. Chris might have explained at the beginning of the talk this evening, we're actually, the Mars area is actually locked at the moment for safety system testing. So we can get you up to the machine outside of it, but unfortunately we can't take you in there tonight. So we'll show you some of the components and hopefully give you an idea of what's going on. So as I said, if you've got questions, just stop me at any point. So what we're showing up here is a typical Mars pulse. So it's a colour video that was actually mounted onto the side of the machine, and it's been slowed down. So a typical pulse on the machine used to be about half a second. On the new machine, so the upgraded machine, it'll be about up to 5 seconds. And this is roughly the size of the plasma. The diameter of Mars plasmas are about 3 meters across and roughly about 3 meters tall. So sort of maybe a wee bit smaller than this. So probably the first thing you'll notice compared to Jet is it's a smaller machine. The other thing you're probably going to notice as well is the shape of the plasma. It's a Tokamak just like Jet, so we use magnetic fields to keep the plasma in shape, and we've got a big transformer in the middle to heat the plasma up. But unlike Jet, we've got more of a sphere shape to the plasma. So it's a more compact plasma, sort of squished in, and it has this more sort of like an apple sort of shape. And it means that rather than a big hole like in the middle of a donut, where you've got a big transformer passing through the middle, on Mars it's more like a core of an apple going through the center. So it's all the same bits, just sort of squished in. That's where Mars really differs, is that it's a spherical Tokamak, so the plasma shape is different. The advantage is that by making your plasma more compact like this, is that it's more efficient. So for a given amount of electrical power going through these magnetic coils, we can get much stronger magnetic fields and better confinement. But the disadvantage is that engineering really, is that you need to put all the same equipment into a much smaller area. So you have to really design things to be very well insulated and also much more compact. So it becomes much more difficult, especially if you're looking towards making something like this for a power station, where you need to have additional shielding and all sorts of other equipment protecting your coils. It becomes even more difficult. So as a result, this is much more of an advanced concept in terms of, sort of ideas for generating power. glow, again, is similar to what you would have seen on jets. It's the hydrogen plasma. The glow on the outside is sort of where the plasma is actually the coldest on the edges. In the background, you can sort of see these coils. So they're the magnetic field coils that we use to contain and shape the plasma. And then, so during the course of a pulse, what's happening here is that in the beginning of the pulse, the transformer is starting to drive current through, heating the plasma up. And then the magnetic coils on the outside of the plasma are actually pulling the plasma around into shape. And then there's also coils in the bottom and the top that are actually stretching the plasma out to our exhaust sections, so the diverter sections of the machine. So a bit different to jet. On jet, you've just got a diverter or an exhaust section on the bottom of the machine. On Mast, we've also got one on the top, so it's symmetrical, so the top and bottom. It's just, the reason why Mast has this is because it's a smaller machine. It's a lot easier for us to put a diverter on the top of the machine. It doesn't weigh the machine down that much more, and it's quite a simple sort of configuration to be able to run with. You can see as well, there's quite a sharp little X forming on the bottom here, on the left and the right hand side, and also the top and the bottom. So that's what's called the X point of the plasma. And that's actually where the magnetic field in the plasma is sort of spiraling around and around, and the plasma is actually cooling quite a lot as it passes through there, so it becomes quite bright. And before it goes down, it hits surfaces on the bottom or on the top of the machine. During the course of the pulse as well, you keep seeing these flashes occurring, and there are instabilities occurring in the plasma. So when those occur, you'll see a huge amount of light coming off, and then you'll see all these sort of lines, all these big sort of filamenty blobs starting to appear. And what's happening there is the temperature and the density in the plasma are building up to really high levels, but then it suddenly collapses. And what's happening then is all the plasma is being shot out from the core. As it comes out, rather than going in random directions, it follows the magnetic field, and it gets directed to the bottom or the tops of the machine through the diverter sections. And the pattern that you can see there is the magnetic field inside the machine. So it's very similar to if you did experiments at school where you have a magnet, if you put a piece of paper over the top and you sprinkle iron filings over it, and you get that nice pattern forming, you can see the magnetic field. What you're seeing in there is the magnetic field forming in the plasma as well, and giving you an idea of where the plasma is actually going to or being directed. So we make use of that magnetic field to actually define the plasma. Because the plasma is made up of positive and negative charges, it'll follow those magnetic field lines, and that's how we define the plasma and keep it in shape. So Mast has been running ran since about 2000, and since 2013 though, we've been upgrading the machine, and I'll explain a little bit more about the upgrade when we're looking at the model later on, but this sort of wall along here is just to show you some of the construction phase. The machine is normally kept, or is currently in that blockhouse, this white building to your left, straight ahead of you, the concrete structure over there. But for the upgrade of the machine, they actually used a crane to pick the entire vacuum vessel up, and it was craned over to the side here, and you can, later on you'll be able to see where the structure is. And they took the whole vessel apart, and you can see here some of the construction sections. So the vacuum vessel was taken off here, the top and bottom lids were taken off, and then the new coils and everything was assembled outside, and then the vessel was taken back in, and then all the components were dropped, the top and bottom lid sections were put back on. So in total now the vessel weighs about 120 tons. So it was actually too heavy for the entire vessel to go in one go. They had to take the top and bottom lids off and do them separately, because the crane's only rated to about, I can't remember what it's rated to. It's 100 tons or something, just around 50 tons or something. So you couldn't have everything in one go, otherwise it would have snapped it. But this gives you some idea. These are some of the magnetic field coils that are used for shaping and controlling the plasma as well. And when we go over to the model, I'll show you some of those and how they're sort of set out and laid out as well. So looking around here as well, you can see some of the components. These are the graphite tiles inside the machine, center column that's going through the middle, and then just some further sections just showing how it was all put back together. But we'll go and have a look at the main section. Actually kept behind us here in the bunker, so think of it as sleep. So for safety commissioning, so we're hoping to start running the machine again by the end of the year. So at the moment they're at the stage where everything's been put back in, but they're now testing all the safety systems around it. So as a result, the safety systems guys have to leave the area locked at night because it takes them about 2 or 3 hours in the morning if they unlock it to then go back through and do all the safety checks and stuff. So they told us that it's just too painful at the moment for them to do that. So this is as close, unfortunately, as we get to the machine. But you can see the crane here. That was what was used for lifting the vessel out. You can see these concrete blocks on the wall here, the white ones, were actually removed so that they could lift the whole vessel out and drag it over. So it was too big to actually lift all the way up over the roof. But we've got some of the best bits of the machine out for you to see. So this is the centre column of the old machine. So I'll step back so you can see it. So you're looking at in the middle there, the brown section is the transformer. So we're talking about why in those videos that you can see in the control room, there's a big column in the middle of the machine. That's what this column is. So the middle section, the brown bit, that's all it is a basic transformer. So it's just a coil of wire. And it works just like the transformers that you've got in your sort of laptop charger or your phone charger work. So you plug those into the wall where you've got 240 volts in your power socket, and they normally step the voltage down to 10 or 12 volts or something like that, and then you can charge your laptop or your phone with. Our transformer works the exact same way. It's a coil of wire, and it operates several thousand volts. This one can take about 50,000 amps of current, so it's a few more amps than your transformer at home probably is designed to go with. But the idea is that the plasma is the second transformer coil. So normally with the transformer you've got 2 coils of wire sort of wrapped around or next to each other. In our case, there's this coil of wire, and then the plasma, you can imagine, is a single loop. And what this transformer does is steps the voltage down, but then the plasma then drives current through the plasma. And in the case of MAST, it's about 1 million amps of current that gets driven through or induced in the plasma. And that's where MAST gets its name from, megaamp spherical Tokamak. So it's this transformer driving 1 million amps of current through the plasma. And that current is one of the main ways that we heat the plasma up. Because that plasma, I guess if you put 1 million amps through anything, it's going to get quite warm. So when you start putting 1 million amps through current, the hydrogen gas that we've got in the machine, it gets very hot very quickly. And that's how you get to the temperatures that we do for the fusion reactions in the machine. What you can also see on the top and bottom, you can see these fingers on the bottom of the top section. They're the main magnetic field coils for the machine. And we'll have a look at those later on. But essentially, if you imagine the cylinder of the machine, essentially it's a cylinder with a coil of wire wrapped around it. And I can't do it with this piece of paper, if you bend that back into a donut shape, all those coils of wire have to pass through the centre, and that's what you can see here. But those fingers are designed to take about 100,000 amps of current. So that passes through the centre column. Then on top of that, you've got the transformer, they're wrapped around it with about 50,000 amps of current. And then you've also got cooling water passing through the coils to help keep them cool when they're running. So it's sort of quite a lethal combination. You've got very high currents, high voltages, you've got cooling water, and you've got very strong magnetic fields, up to about 0.6 Tesla. So there's huge stresses on this part of the machine, and this is one of the reasons why spherical Tokamaks are so difficult to build, is that we've got all this engineering that has to go into a very small, compact area. So there's a lot of calculations and a lot of really advanced sort of design and material work that needs to go into building that as well. But that gives us some idea also how big the machine is. So it's roughly about 4 meters tall.
Is that the most expensive bit in the machine?
One of the biggest single bits. The coils that we have as well are about 4 meters diameter, and again they're very expensive to manufacture and make as well. As you come over to here, you can see some of the diagnostics as well that we've got for the machine. So we're really lucky with MAST in that we've got a lot of equipment for doing the measurements with. This is probably a piece of one of our most expensive bits of kit. So we can't stick anything into the plasma to do measurements with. If you stick a probe or anything right into the core, it just stops the shock and it'll melt. So as a result, we need to look at what's coming off the plasma to understand what's going on. What we can do as well is actually if we fire a laser beam into the plasma, and if we look at the light that gets scattered off the plasma, that can then tell us a lot about how dense and how hot the plasma is, and that's what this system is designed for. We actually fire a laser through the plasma, and this is one of the collection lenses that captures the light that's coming off the plasma. And if we measure, so the laser light that goes in, we know the frequency of that because it's very precise. If we measure the frequency of the light coming off from here, if we compare the two, we can then work out how fast the plasma is going, and it's using the Doppler effect. So it's very similar to if you ever hear an ambulance coming towards you, the sound's very different to when it sounds higher pitched coming towards you compared to when it goes away. Similar effect if you're listening to F1 cars going around the racing track. It's the same effect here. By comparing that frequency or the pitch, you can work out effectively how fast the ambulance is going or how fast the plasma is going, and work out how hot it is. Some of the other, so that's one of the most expensive pieces of kit that was funded by the University of York. We go right through from very expensive, right through to very small, delicate, well, not delicate, very easy to look at. I'll pass these around. These are small bits of measurement equipment. The coil that we have is a magnetic field measurement coil, so I'll pass that around so you can see. And you can see that coil is just designed so that when the magnetic field goes through it, and as the field changes with time, it induces or generates a current in that coil, and we can then use that to work out how strong the magnetic field is at that point. And that then tells us magnetic field, and we position, there's probably several hundred of these around the machine. That tells us the magnetic field strength at different positions, which then helps us work out where the plasma is, and then we can then use that into computer calculations to work out how to control and position the plasma. The little black probe that you can see there is just a small graphite probe. So it's like a graphite, like your lead pencil, essentially. But we can, because the plasma is made up of positive and negative charges, if you apply an electrical voltage to that probe, you can either repel or attract the plasma away. And measuring how much voltage you're using to do that tells you how much energy the plasma has, how hot it is. And then if you measure the current of the plasma hitting that surface, you can then work out how dense the plasma is. So there's little, I'll take them off you if you want. Yep. So these little probes actually allow us to measure the density and the temperature at different positions in the machine. And then just by doing simple electrical and voltage measurements. And we've got about 650 of these positioned around the machine. And that tells us density and temperature in all different positions. And again, just by doing that, you can then just do some simple calculations to then work backwards to work out what density and temperature is around the rest of the machine, further back into the core. And then again, we feed that into computer simulation models. So just quickly, this is one of our diagnostic ports. There's about 40 of those on the machine. And again, these are just some similar examples of just some of the tile holders, some of the heating, neutral beam cooling equipment and stuff that we've got on the machine. So I blabbed on for too long, sorry. Yeah. So we'll head over to the next stop, but if you've got any questions, please hold on to them and we'll head over to the next stop and you can ask them next. Experiments back in the 1970s and 80s. It's got all the same elements that masks and jet have, so and it's been stripped back a bit though. So this is the vacuum vessel, and what you would have had previously is you would have had a coil of wire wrapped around here, and that would have acted as an electromagnet, so you would have put a current through that would have generated the main toroidal magnetic field. In the center here there would have been a big transformer, just like the one you saw lying on the floor before, and that would have been used to inducing the current that goes around the plasma and heats the plasma up. And then these other ports would have been used for injecting gas or for diagnostic measurements. So it's got all the same ideas that you have in a bigger scale machine. And if there's devices all like this all around the world, in small in universities and other research laboratories. If all you're interested in is the plasma physics of what's going on, then these are really good devices. The reason why we have to keep scaling up though is that if you want to generate power, you need to confine the plasma. And the confinement really scales with volume, because the bigger the plasma is, effectively the longer it takes for it to get out of the magnetic bottle that you're holding it in. And also the volume of the plasma is going to determine how much power you generate as well. The bigger the volume, of course, the more fusion reactions you've got, so the more fusion power you can produce. So that's why, but the trade-off, of course, is as the machine becomes bigger, it becomes more expensive to produce big coils. And also you need more power to go through those coils to actually generate the fields. So this is why there's such a balancing act. Machines like ITER and JET are using technology that's really at the limit in terms of size, but they're pushing those sorts of boundaries because you need those big volumes to get enough fusion reactions out. The other avenue that things are starting to take now is people are interested in, can you use smaller machines like masks to generate power with? And to do that, you need to push the plasma performance up to very high levels. And that's where sort of people are trying to study, can you do that? Can you design materials or transformers, power supplies and equipment that can withstand the sorts of high levels of radiation that you're going to generate in a machine like that, where it's a lot more compact as well. So it gives you some idea of how things are going. Other components that we've got the big what you can see lying on the floor here is actually a broken transformer. So this is one that broke during the first year of MAST's operation, back in around the year 2000. And you can see this is the same design of transformers you saw near the blockhouse, near the machine area. You can see that it's 2 turns of wire wrapped around twice, so to make 4 sort of layers of coils. And the little holes that you can see in between in the copper are designed for the cooling water to go through. Around each piece of copper you can see as well is a very thin layer of insulating resin. So that's, you can imagine that's actually where the fault occurred. One of those layers basically broke down, and as a result it created an arc sort of sparking, which then helped erode even more and then caused quite a major fault. But then, so it gives you some idea of how complicated the transformer is, and then passing through the middle of that are the main magnetic field coils. So I'll pass this around to give you an idea of weight, and embedded into the tile, the graphite probes. And again, they're stacked like this so that you can then get density and temperature measurements at different positions, and then you can work backwards. And the physics of what we do with these probes, again, it's just simple electrical current and voltage measurements. And then just by doing some basic calculations, you can then work backwards up the magnetic field from this point into the core, up into the edge of the plasma and then to the core to work out temperatures and things. So yeah, we do, on one hand, you do very complicated physics with some of the scientists here do for simulations and understanding, but then we also do exact same physics that you would have done at high school or in your science courses about electricity and magnetism and currents and voltages to help us understand what's going on. So it's actually quite nice. So the science that you do at school doesn't go to waste here. You can apply a lot of it, which is really nice. So for a power station comparable of Didcot power station size, so producing about 1,000 megawatts of power, you'd be looking at needing probably several hundred kilos of fuel per year of deuterium and tritium fuel. So that sounds like quite a bit, but that's in comparison to the amount of coal or gas that the power station uses, it's much, much less. There you're looking at hundreds of tons of fuel that you would need per year to keep going. So the amount of fuel is much smaller because the energy released per kilo is huge in a fusion reaction. The trade-offs though are that deuterium is relatively easy to get from seawater. You can distill it out. Tritium is the limiting reagent though for us, because tritium it's hydrogen with 2 neutrons in it, but typically it's only produced in nuclear reactors at the moment. There's only 1 or 2 reactors in the world that produce it. But the advantage, the hope is, or the current focus is that you can produce it from lithium. So ITER will be one of the first machines to test this by having lithium blankets around the side of the machine. And as the neutrons from the fusion reaction pass through that, it actually produces tritium as a byproduct in the lithium. It converts lithium in, because lithium isn't very far away from hydrogen in the periodic table, it's just 1 across. So you can easily produce tritium from that. So the idea is that you can breed tritium in the lithium blankets. So that's the hope is that you would have that as a source of your fuel for the future as well. In addition to, if necessary, you could use other fission reactors to produce your fuel, but primarily it would be from the actual topic. So the last stop here is looking at a model of the internal parts of the machine. So this is the actual internal sort of structure of MAST. But this is a scale model. So this is the actual size of what's inside the Tokamak. So this is the main, where the transformer would sit. So that's the one that you saw lying on the floor next to the blockhouse. That sits in here, and it would normally be covered in the graphite tiles, like you saw just before we went upstairs to look at the components. So that sits in the middle here. On MAST, the plasma radius comes out to about here. It's about 1.5 meters. And again, the plasma is about 3 meters tall, so roughly 3 meters across. So the volume-wise, it's sort of like the volume of a small sort of passenger car. In terms of temperatures, the core of the plasma here, so what I'm pointing to, that'll be about 20 million degrees Celsius in MAST. So in comparison, the sun is about 15 million degrees Celsius in the core. So similar temperature to the core of the sun. And then coming down to the edge of the plasma here, it's probably a few thousand degrees Celsius. And it's really quite a steep gradient. The edge of the plasma gets out to out here. And then the temperature drops from down to just below 1,000 degrees in the outer sort of few centimeters of the plasma. So it's quite a steep drop off. Those are the temperatures, so we need to get to quite high temperatures like that to actually force fusion reactions to occur. On MAST, we don't get a huge number of fusion reactions occurring because we don't use tritium, and also because that temperature isn't hot enough. It turns out to get a lot of fusion reactions, you really need to get to temperatures that jet has, about 150 million degrees Celsius. And it's just sort of, yeah. So as a concept, I can't even fathom what that is. So it's very, very hot. But it's important to realize that it's not the entire machine that gets to that temperature, it's only the fuel. And on a typical pulse on this machine, it's only about 1 milligram of gas in there. So you could hold that, it's like a postage stamp, right? You would barely feel it. But that's how it can get to such high temperatures. So the transformer gives about a megawatt, so a million watts of power. The 2 particle accelerators we have on the machine give about 2 megawatts each. So we can put about 6 megawatts of heating power, so 6 million watts of power into about 1 milligram of gas. And that's how you can get to such high temperatures in the machine, in the plasma. And so to actually cause those fusion reactions to occur. Looking around the rest of the machine, you can see that we've got all these other red coils. And again, these are electromagnets. So we put currents through these coils, and that allows us to shape or control the plasma. Because the plasma's got this 1 million amps of current going through it, if you put currents through these coils, they become magnetic as well, and you can push or pull the plasma around and shape and control it. So the P coils are colloidal ones for sort of radius control. The D coils are our diverter coils, and this whole exhaust or diverter section is really the focus for the upgrade of the machine that we're going through at the moment. If you remember back to what you saw on Jet has a diverter or an exhaust section like this as well, but it's just an open V sort of structure. So for the upgrade of this machine, what we've done is they've put in a new sort of nose with additional coils here, and the idea is that you shape or control the plasma and push it further down and away from the core. And the reason we're doing that is we're trying to separate the core from the exhaust section. Basically because they're 2 opposite sort of aims, really. In the core you want to have the plasma as hot as possible. In the exhaust you want to have it as cold as possible so that you don't damage the machine. And you don't want the 2 to mix. So the plasma, you can see it's a very narrow space in here. The plasma actually acts as a plug to stop the cold gas getting back up. And we've also got, you can see these yellow baffles through here to stop the cold gas leaking back up into the top section of the machine. So in terms of positioning, these coils are designed to position the plasma to within maybe 1 or 2 millimeters accuracy in terms of positional control. That's all done by a computer. So we've got cameras that track the plasma edge, and they can then decide to push or pull the plasma in different directions to help us shape and control it. Again, we can use those little magnets, those little coils that you saw as well, that you were picking up. They're positioned all around the machine. And again, they give real-time information to the sensors, the computer's control system, saying telling us what the magnetic field is at different positions, and we can work out then where the plasma is, and then that allows us to shape and control the plasma by changing the currents in these coils to shape and do that. So this can all be done in sort of millisecond timescales to control it. It works to a certain extent, but of course if the plasma becomes too unstable, then the coils just can't respond quickly enough, and then we'll lose the shot. So that's sort of one of the trade-offs that we've got. But again, when the plasma reaches a steady state, you can get to really high accuracy and quite high repeatability of shots as well. So you can keep doing the same shot again and again, just so you can repeat experiments and actually just vary one thing at a time when you're doing the experiments as well. Are there any questions looking at the machine?
When you say cold gas, what's the temperature of the cold exhaust
below
gas?
1,000 degrees Celsius.
Right.
And when the plasma, when it comes out from here, because the magnetic field's not perfect, it eventually leaks out here, and it travels about 30 meters to come down here, and eventually hits these surfaces, and then it gets neutralized. It goes from positive and negative charges just into neutral gas that can then be pumped away in the pumping system. So ideally it should be below 1,000 when we're running the diverter. So no, this machine, no, we produce probably at a typical mass pulse there'd be kilojoules of energy, so Mars bar levels of energy coming out of the plasma, simply because we use a much lower temperature than, well, it's high but not high enough, and also we don't run with tritium in the machine. So really the focus for this machine isn't power generation.
So it's just research.
Yeah, just research, yeah. And really it's mainly for us now, the upgraded machine is really this focus on the exhaust section, and also generally understanding how spherical tokamaks can be used. So this idea of if you make, rather than having a donut-shaped plasma, if you squish it all in, make it a sphere, can you make it more efficient
can you get better performance out of the machine? How do you tweak it to do that? Because I mean, we were lucky that the government's given us some additional funding to help try to take this concept further as a power station design, but it's very much in its infancy at the moment. Definitely for early generation power stations, you're looking more at machines like you saw earlier, a jet design sort of machine at the moment.
And when will we see that?
Okay, you've got a camera running, so I don't realise I'm going to commit myself by saying it. So it really depends on the levels of commitment the government and other research bodies are willing to put into it. I think at the current level, I would have said probably 2060, 2070 to get demonstration power onto the grid. I think ITER will get up and running 2030s and hopefully demonstrate power ability to produce more power than goes in, and up to 10 times more power than goes in. And as that's happening in the 2030s and 40s, I think they'll be starting to design the first demonstration power plants. But it's tricky to do because you really need ITER's results to help you inform what's going to happen. And until that happens, I think it's really tricky to predict exactly what will happen. I think if there is a drive to push fusion power along, so let's say if the price of uranium or the price of coal and gas shoots up massively, and there's a huge demand, or if there's a demand from the environmental lobby that the levels of pollution being created are just too much, and the fusion really needs to get going, and people are willing to fund more, essentially to fund a second ITER or to fund more demonstration power plant designs, then I think you can speed it up. But I think at current rates, well, yeah, it's just too hard to predict. So yeah, so, is that non-committal enough, especially for being on camera?
Watch this again in 2060.
Yes, yeah, when I'm retiring, and I'll be very embarrassed to say. But it could all change. It's so hard to predict at the moment. I think the diagnostics we were looking at earlier on, I think, give you an idea that over the last 10, 20 years, the advancements that we've had in the physics of lasers and in materials and engineering and electronics and computing have been such that no one could have really predicted that. And that's given us a huge step forward in how we understand what goes on in the plasma. A lot of the little probes that we have give us an idea of what the edge, but these lasers and these new optics and things that we have really have told us a lot more about what goes on in the core, and I think that's really revealed a better understanding for us. And it's allowed us to get, and also to improve the performance of the plasma so that we're getting to levels that you would want in a power station. So I think we've definitely made huge amounts of progress, but again, it's very, yeah, and hopefully if it goes at that rate, we're going to get even better understanding from computer simulations now as we go forward. So yeah, and then probably it's a good point to say that if you look around our site now, one of the big focuses for us is on training not just scientists, but also technicians and engineers. Because a lot of the work that we're doing now is about designing engineering components to withstand the high level heat and radiation levels that these machines are going to generate. So that's why if you look around site, there's a big materials research area, a big robotics area, and there's the big apprentice training area now as well for helping train technicians for that, in addition to the science teams that we have. So young people in the audience as well. So it's quite a good time to be going through because there's a big push to get new people, not just in the physics side, but also material science, electrical, mechanical, vacuum engineering and things. So if you have any interest in engineering or science, please keep us in mind, and either coming through university or now through our apprentice training schemes and graduate schemes, because there's a lot of really exciting science and engineering going on, and I think it'll only get more sort of interesting as we get towards running the ITER and the demonstration power plants. So it's all, I think there's a lot of work to do, but please don't go away thinking it's never going to happen. I think we're definitely getting closer, and I think hopefully within your lifetime, definitely, the youngest member here, you'll definitely see ITER running and hopefully produce power, and hopefully, I hope to see ITER as well running up and producing power before I retire. I've talked for too much. Okay, so I hope you've enjoyed your visit. If you do have questions, please feel free afterwards as well to email any of us, or to email CCFE, and we're always happy to answer questions or to have you back here for more tours and things. But otherwise, thank you very much for coming.
Thank you.